All right, here we go. Talking about 17.1 and 16.1. Basically, going to be talking about the ocean. We're going to be talking about the atmosphere. So we'll start with the atmosphere. So you can see that atmosphere is mainly N2, or basically it's nitrogen gas, mainly nitrogen gas and oxygen gas, with 0.04% being CO2. So you can see on the right-hand side of the diagram right there, you can see nitrogen gas is basically almost 80%. We got about 21% oxygen, okay, and then the rest is a whole bunch of other little things, okay. The CO2, that amount is going up. The amount of methane right now, as you can see, 0.00018%, which is good, but it is rising. And CO2 and methane are the big greenhouse gases that we're concerned about. So we are still seeing climate change with that little amount of greenhouse gas, like you can see. Okay, it's still CO2%. CO2 is 0.04, 0.00018. That is causing climate change, that tiny amount. So if that starts to increase, we're really, really in trouble. So that's page 466. Moving to page 477, or excuse me, 447. This diagram here, you're definitely going to need to know. Like it says, know this diagram and its details. So there's a lot going on here. So we'll start from the top. Actually, we'll start from the bottom, where we are. Okay, the troposphere, that's where we live. That's honestly, that's got a ton of different molecules in it. That's where weather and climate happen, stuff like that. We get up into the stratosphere, and this blue line you can see is ozone concentration. The ozone, you can see how much of it is in the stratosphere. That's the thing that protects us from like the UV radiation. You can see the temperature when it's really warm. You can see basically temperature in degrees Celsius. Okay, it's basically up here. So you can see it's warm at the surface. We start climbing, that's when it starts getting cold. But above the ozone, it starts to really increase. Okay, then it's going to drop back down and then go back up. There's also another layer up here. It's called the exosphere, EXO sphere. That's basically kind of like when it's starting to get into space, is what that's talking about up there. So the thermosphere you can see is up top, then the mesosphere, the stratosphere, and the troposphere. Now the thermosphere, if you guys have ever heard of auroras or like the northern lights, that happens up here in the thermosphere is where that's going on. Okay, another diagram you can kind of see at the bottom of the page there, the bottom corner, is talking about the amount of molecules that are everywhere. So you can see above 50% of air molecules. So in the troposphere, which again you can see up here, this is where most of the molecules on Earth are sitting down near us, thankfully. It's like oxygen that we need, obviously, and things like that. Okay, you can see the weather balloon way up here. See Mount Everest is like the tallest point on Earth right now. So basically the amount of pressure that's going on. And one of the things I want to point out is the density of air molecules. So like if you're down here on the bottom here at basically zero altitude, you have a lot of atmosphere pushing down on you. So you have a lot of atmospheric pressure, and that's why basically this red line is. So basically, the closer you are to the Earth's surface, the more pressure you have. So as you go away from the Earth, the pressure starts to get lower and lower and lower, and that's why if you fly, your ears pop, because you're having less pressure or there's less atmosphere above you pushing down onto you. So moving to page 448. Think about, I wrote it right there. Pressure at sea level is higher than on a mountain because there's more atmosphere above you. So I'm not really going to go into much detail because I already talked about it, but basically just to write that down. Now what humidity is, at least it's a dry heat. I love that saying. Because like in Vegas, there was very, very, very little humidity, but it's 110 degrees. But personally, I'll take 100 degrees and zero humidity rather than 80 degrees and 90% humidity. It's awful. Absolutely awful. Okay? So, moving on to page 449, talking about the Earth's tilt. Okay, this is what creates seasons. We tilt at 23.5 degrees, and this is what creates our seasons. So you can see like December solstice, Northern America, where we are, we're obviously farther away from the sun, or we're leaning away, so it gets colder. But we go through and we go to June, we're now leaning towards the sun, so it's much warmer. It's obviously different for the southern hemisphere. So like the southern hemisphere, like South America, you can see right there, Brazil's right there for that one student who doesn't know where it is. For them, December, this is their summer because you can see they're closer to the sun at this point. But during our summer, that's their winter. So you can see next thing I wrote here is hot, moist air is less dense and rises, causing a convective circulation process to begin. And we'll talk about weather and climate in a second. But this diagram underneath it shows this really well. So hot, moist air is going to rise because it's less dense. Okay, creates condensation or creates clouds, creates rain. Okay, the excess heat radiates into space. Once this occurs, it now becomes cool, dry air. Now this is more dense, so it drops. Okay, then it starts to get warm and kind of warm up. Then it goes along, picks up the moisture, and then it starts to rise again. And then basically kind of goes what's called a convective circulation. That's what helps drive weather. Now there's weather and there's climate. Big difference between them. The weather is like, hey, it's raining today, versus the climate, we live in a tropical rainforest kind of a thing. You know, like certain area, like there's a desert. It rained once today. We can't be in a desert. Well, no, we're in a desert kind of a thing. So this is like the overarching weather patterns on a yearly or decade base versus a daily basis. So that's why they talk about like the weather forecast for the day. All right, moving to page 450. Okay, so we're going to talk about a warm front and a cold front. And I'm moving so we can see the pictures a little bit better. Okay, so warm fronts and cold fronts. So you can see the warm air is coming in. So this is the warm front. The warm air is coming in and kind of pushing it away. The cool air is moving out of it. Whereas on the flip side, this is the cold front. The cold air, which is lower, is basically pushing the warm air away. There's the cold front right there. Basically, everything's moving from left to right. Okay, it's the same up here. Everything's moving left to right, but the warm air comes in, pushes the cool air around. There's a lot of light precipitation as it comes in, but heavy precipitation when the cold front hits. So if you ever watch the evening news, they talk about like the high pressure and low pressure systems. What they're talking about is a high pressure system brings in the good weather. So to jump back up, this high pressure system, this is bringing in like the nice kind of warm air and warm conditions and warm weather or good weather. The low pressure system at the other point, when that comes in, whole bunch of cold air, lots of precipitation. So it's cold and it's rainy, or it's cold and it's snowing. Now the other thing I have on here is what's called a temperature inversion. So normal conditions are like this. So the sun warms the surface, the heat radiates up from the surface, there's some mixing going on, it's warm at the surface and cool as it goes up. However, a temperature inversion is here. So from a city, think of LA. LA is surrounded by a bunch of mountains. So the pollution comes up, the pollution doesn't really have anywhere for it to go, so it traps the cold air underneath it. So the warmth, the sun can't get down all the way to the bottom and warm it all up. So this is what's a temperature inversion, or it's cool down here and warm up here, which is the opposite or inversion of what it should be. So like I talked about in the sticky note up here, above air above is warm, air below is cold, and it doesn't allow the vertical mixing. And this part right here, vertical mixing, that's really, really, really important for weather and climate and wind patterns and whatnot. So moving to 451, as warm air rises, it condenses into clouds and rain. So it talks about the different kinds of cells. So you can see it right here. The warm air, like we just talked about the convection currents, the cool air comes down, it warms up, it picks up moisture, it rises, rain falls, cool, dry air, then it drops back down because it's heavy. And just goes on again and again and again and again. Okay, at this 30 degrees north, which you can see is basically right about there. 30 degrees south is right about there. It's arid. Arid means that it's really, really, really dry. What happens in dry areas? There's a desert. That's basically what happens, because a whole bunch of cool, dry air comes dropping down. So there's no moisture in there. There's no rain. There's no precipitation. Okay, so there's what's called the Hadley cells. The Hadley cells are the ones basically that are based on from the equator. That's the Hadley cells. The next one up is the Ferrel cells. Then there's the polar cells. Polar, I'm confident you guys can remember, is related to the poles. If you can relate, just literally, if you can remember one of the other two, that will help you figure out where the other one goes. So the polar cells are the most north, Ferrel cells are in the middle, and the Hadley cells are near the equator. So there's also the trade winds, the westerlies, and the doldrums. That's dealing with wind is what that is. So you can see the trade winds are right here. Okay, you can see they're basically coming down, they're moving from east to west. Okay, there's also the westerlies, and the wind currents are named for where they're coming from. So the westerlies are coming from the west, so they're going from west to east. The doldrums are basically right in the middle, where there isn't any wind. So when they were like colonizing North America, when they would come across the ocean, they were basically trying to avoid the doldrums, because back before they had like engines, if there was no wind, you don't move. And so you just get stuck in the doldrums is what they would talk about. All right, there's another thing called the Coriolis effect. This thing might be a little bit more difficult to understand. So the Coriolis effect causes global wind and water currents to bend. So what it says here. So let's talk about, starting right here. I hope I'm on the screen, I am. As Earth rotates on its axis, regions of the planet's surface near the equator move west to east more quickly than regions near the poles. Or basically the whole Earth is spinning. So if you are trying to come, if you are right there and you are trying to go due south, since the Earth is spinning, it's going to make you kind of naturally turn this direction. Okay, because up here you aren't rotating as fast as you are right there. So as you go south, you start to bend. That's what's called the Coriolis effect. And that's why instead of the trade winds just going basically just straight south, they turn. It's the same thing for the westerlies. They try to go north, but since they are moving quicker than up here, they move over. They bend. All right, moving to the next page. Okay, we only got one little bit on page 452 here because you can see we jump on to the next section. So the last thing we're going to talk about is hurricanes. Okay, so hurricanes, warm air rises quickly. Like I was saying, it's less dense. So warm air rises really, really quick, pulling in other air really fast. So the Coriolis effect makes it start to spin, pulling in more water, pulling in more air, and then it happens faster and faster and faster and faster and faster. That's why hurricanes can start to build if they spend time over the ocean. Then, once they hit the land, there's a whole bunch of rain that happens, and the hurricane dissipates. Because instead of it being over ocean, where this whole thing can happen faster and faster and faster and faster and faster, it gets over the land where there's less water, and so the land doesn't cool or warm up as fast, so it dissipates. Okay, over the land, you get a tornado. It's a similar, but now you just don't have the water involved in it. So like hurricanes pulling more water, they will make ocean rise. They'll have what's called storm surge, where the ocean, like the sea level will rise into the land and cause flooding. Alrighty, so now we got to move to 16.1. Now we're moving to page 416. You can see it right there. We'll talk about the oceans. So obviously the oceans are our most important resource. Everything is based on them. Okay, the ocean helps soak up some of the CO2 in the atmosphere, causing climate change to try and be avoided because they're soaking a lot of it up. Okay, algae by far creates the most amount of oxygen for us. So everything is based on the ocean. So they receive every input, good and bad, from every activity that occurs in our world. So all the pollution that we create on land just runs down into the ocean. They soak up everything for us. So we talked about seafloors, and we talked about this mid-Atlantic ridge already. Okay, Marianas Trench is the deepest point in the world. They're just examples of what's going on. You can see seafloors are anything but flat. big changes going on inside of on the ocean. Okay, 418. Obviously, the ocean is salty. Okay, why that is? The water is going to evaporate, but the salt doesn't. The sediments from the runoff stay there. The weathering of rocks drains down into the ocean. So the upper layer of the ocean creates a lot of oxygen for the world. Like I was talking about, that's where a lot of our oxygen comes from, is the algae. We have no oxygen, we get no animals. Okay, there's also these things called hypoxic dead zones, like the Gulf dead zone, that kind of thing. Now we also got surface activity only affects the top 150 meters of water. Then the water becomes much, much, much dense with very little movement. Okay, the ocean temperature is also very stable. It's only about a 10 degrees Celsius shift throughout the entire year. So it's pretty stable. And so luckily, the ocean keeps most of the earth and climate kind of stable. Okay, so this next page, 419, very important, talking about ocean currents. Now, like it says there, I'm not going to ask you about the current names. Okay, so like the South Equatorial and the North Equatorial and the North Atlantic and the Azores. I'm not going to ask you about the names of anything, but you have to be familiar with how they affect things. So, an easy thing to talk about their effects is why is the northern part of Canada really, really, really cold, but the same latitude, Europe's pretty warm. The reason for that, okay, the North Equatorial currents or the Caribbean currents, basically they're bringing warm water up. And think about the east coast of America compared to the west coast of America. Their water is warm, our water is cold because our water is coming from Alaska. Okay, that warm water goes across the Atlantic, and that warm water keeps it so the weather over here is warm. That's a big deal because water can transport heat really, really, really well. But at the same point, let's jump over the Pacific. Okay, we got warm water, warm water. Oh, it's nice and warm, nice and warm, nice and warm. Japan's nice and warm. Going up to Korea, nice and warm. Oh, wait, never mind. As it starts to go across, it cools down. Okay, now we got all the Alaskan water coming down for us. Now our water is really cold. That's why over here in Washington, over in Washington, California, the guys wear wetsuits typically. Over on the East Coast, they don't, okay, because the water is really warm over here. All right, so this one talks about this case behind, or this science behind the story is talking about this dead zone. So you can see like Louisiana and Texas, Mississippi rivers dumping out. That's that Gulf of Mexico dead zone. All right, so like I said there, big bold letters, know this page. We're on 422. The upwelling and downwelling, the transport of heat via water. Really important things going on here. Okay, if this stuff starts getting messed up, we're really, really, really in trouble. Okay, I'll push that a little bit higher. Okay, so let's talk about some real basic stuff. Okay, warm water comes up, then it starts to cool off, and then it sinks. Basically sinks down to the bottom of the ocean, or really low, it starts to really kind of go along. Cold, deep current. Okay, comes up, starts to get warmed up as it's going across the ocean again. This upwelling and downwelling is really, really, really important stuff. Because this part, it kind of deals with El Nino and La Nina and stuff like that. So, here's El Nino and La Nina. Okay, or I should just say El Nino and normal conditions. So, normal conditions. Upwelling of deep cold water. Okay, here's Peru, here's Indonesia. Like basically think of this as the Pacific right here. There's North America up there, there's Asia over here. So upwelling, basically the really cold, nutrient-dense water rises in Peru. Then the winds push it across the Pacific over to Indonesia. Okay, and this is where like the really warm water over here. Okay, lots of rain happens over here as well. Okay, but the fisheries over here on the west coast of South America are really strong because you get a whole bunch of nutrient-dense water rising that's really cold, has a whole bunch of stuff for a whole bunch of life to happen. However, during El Nino, that upwelling is no longer there. Okay, the reason for it, instead of the winds pushing everything across the Pacific, now the winds is kind of not as strong. So the wind is coming, or the current is now coming this direction. So that upwelling stops. So these years for the fishery or the fish industry in Peru and the west coast of South America is really, really, really poor. So I'm going to try and do a demonstration for this as well, but basically the understanding for normal conditions, there's upwelling. Lots of nutrients pop in. El Nino, that upwelling stops, is basically what's happened. All right, I know this was a long one, but leave some questions for me so we can talk.